Okay, now we get into the really cool part of vectors. So, given certain information of a vector, can we find its components? So, uh, this diagram here on this screen should look very familiar to you if you're taking trigonometry. Okay, this is a unit circle. The central angle there, and drawn in a standard position, is alpha. We could just use theta too. It doesn't matter. It's just a variable. It's interchangeable. Okay, and we know it's a unit circle because the radius is 1 and we're starting at the origin. So in this case, right, we could say, and this should be, again, if you're taking trigonometry, this should not be confusing. The coordinates of this point on this unit circle are cosine of theta, sine of theta. Okay, unit circle. And the reason that this is the case is because the radius is 1. If we had instead, let's say the radius wasn't 1. Let's say the radius was r. Okay, well then we have to go back and look at what's the definition of sine and cosine, right? So let's cosine first, right? The cosine of theta is equal to the opposite side divided by the hypotenuse. So in the case of our unit circle here, that would be the opposite side with respect to angle theta is, sorry, not the opposite, I'm sorry, this is the adjacent side. Okay, the adjacent side. So the adjacent side with respect to angle theta is the x-axis, is along the x-axis. Okay, so it's the x coordinate here. The hypotenuse is r, so x divided by r. So if I wanted to know if this was no longer 1, right, the whole thing with the unit circle is that r was equal to 1, so cosine of theta was just x. But when we're dealing with these hypotenuses that are greater, hypotenuses that are greater or different than 1, say there are, well, then we have to say, all right, x is not cosine theta, it's r times the cosine of theta, right? Take cosine of theta is equal to x divided by r, multiply both sides by r, and you'll get this, right? X is equal to r cosine theta. By the same thinking, right, the sine of theta is equal to the opposite divided by the hypotenuse, or in this case, the y value, the side opposite the angle theta, opposite, divided by r. Well, again, solve for y here, we get y is equal to r times the sine of theta. So if we were given just anything, we wouldn't say, if this wasn't a unit circle, now it was just some circle, we would say r cosine theta is the x value, and r sine theta is the y value, okay? This should be fairly natural. It's not much of an extension. We've talked about this before. Okay, now watch. Okay, look, now we don't just have an angle inside of a unit circle. Now we're talking about a vector. Okay, specifically, let's say we're still talking about just a unit circle. If we're just talking about just a unit circle, the unit vector u, unit vector, meaning its magnitude is 1. Look, magnitude of 1. Okay, its components, you can talk about its horizontal component as cosine theta, cosine alpha. You could talk about its vertical component as sine alpha. Now, what's the difference between what we just put here and what was on the previous slide? It's that r value, right? So if we had any, now let's say it's not a radius of 1, or it's not a magnitude of 1. Now it's a magnitude of something, right? This is like what r was in the previous slide. So in this case, like imagine it was r cosine theta I hat plus r sine theta j hat. We'll factor the r out. Cosine theta I hat plus sine theta j hat. Look, that's the same thing we have here. Hey, this is foundational. Okay, this is really all you need to know when it comes to given a vector's magnitude and direction, what are the components of that vector? It's just r cosine theta, r sine theta, okay, where the magnitude times cosine theta, the magnitude times sine theta, and it's common to represent it with the magnitude factored out like this, although it's obviously, if you multiply the magnitude into both of these things using the distributive property multiplication across addition, you'd have the same thing. It's just a different simplification. Okay, so how do we apply this? Right, Cody Bellinger threw a ball from right field at a speed of 84 miles per hour at an angle of 30 degrees from the ground. Express the velocity vector of the ball in terms of the horizontal and vertical speeds. Okay, maybe a quick diagram would be good here. Okay, so Cody Bellinger on the Los Angeles Dodgers. Okay, and he's going to throw this ball at, I say, an angle of 30 degrees. So here's the ball over here. He threw it, and this angle is 30 degrees, and it's going at a magnitude, right? The magnitude of this vector. Let's say the vector is vector c for Cody. Okay, the magnitude of vector c is 84 miles per hour, and it's going at an angle of 30 degrees from the horizontal. Okay, so this should look familiar to the diagram we just had. So if we wanted to know what are the horizontal and the vertical components of that vector, well, we would just break it up into the horizontal and vertical components. So vector c would just be, we take the magnitude 84 times cosine of 30 degrees to get our horizontal component, and 84, the magnitude, times sine of 30 degrees to get our vertical component. Now, in this case, because 30 degrees is one of our really common angles on the unit circle, and we know, not just unit circles, just common angles, and we know their known exact values, like we can express them as, you know, with radicals and stuff. We can just say cosine of 30 degrees, that's square root of 3 over 2. So 84 times the square root of 3 over 2 gives us 42 times the square root of 3 I hat, and then 84 times the sine of 30 degrees, sine of 30 degrees is 1/2. So 84 times 1/2 is 42 j hat. Okay, so those are the components of the throw, right? The horizontal speed and the vertical speed of that throw. All right, now this next problem is fairly involved, but doesn't include anything really drastically new, just some definition stuff. But all this same stuff where we do this cosine, this r cosine theta, r sine theta, or the magnitude times cosine theta, magnitude times sine theta to get our components, it's all the same thing. Okay, so static equilibrium. First of all, what does this mean? Okay, static means not moving. Okay, it's not moving. Equilibrium means it's a situation where there's no, it's equality, right? There's no, everything's balanced. Okay, so in this diagram, what that means is that this weight, this 10 Newton weight that's being suspended by these two cables is not moving. Okay, now what we want to do is find the tension in both of the ropes, okay, both of the cables. And we can do this, right? This looks really complicated, but really all that's happening here is just the same thing we just did, but it's a little more involved, but it's the same thing. Okay, so one thing you can do, and I strongly encourage that you do this, is to break down, look, this is clear, this is a vector, right? That's a vector. There's a force in that tension, in that cable. There's a force in this cable, okay? It's a vector. We can break down each of these into a horizontal and a vertical component, okay? And you literally just draw right on top of this thing. It's not necessary, but you could totally do it. Okay, now we have to know what's be really important. If it would be really great if we can get that angle and that angle. It's actually given to us in this problem. Vertical angles in geometry, we know if that's 30 degrees and this is also 30 degrees, and if this is 45 degrees and this is also 45 degrees, right? Because that's a right triangle, that's a right triangle, that's a right triangle. Okay, so if that's being said, let's say what would this be? What would this be right here? Well, this would be the magnitude T2 times the cosine of 30 degrees, right? Just from what we did previously. This then would be, over here, would be T2 times the sine of 30 degrees, the vertical component. Okay, we can write I hats and j hats there if you want. You might as well. Okay, so I hat, j hat. Right. And now, on the other side, by the same exact thinking, this would be the magnitude of the force in that cable, the tension in that cable, T1, times the cosine of 45 degrees, I hat, and T1, the magnitude, times the sine, 45 degrees, j hat. Okay, now, there's a step here that you'll learn in physics or you'll learn it in engineering, and it's called creating a free body diagram. Now, this is not necessary at all, but if you consider the point at which these two cables attach to this weight and talk about all the forces that are acting on that one point, well, it would look something like this. Okay, we'd have this point, and we say, all right, on that point, there are vertical forces going up of T1 times the sine of 45 degrees, and T2 times the sine of 30 degrees, right? From right here and right here. And there's also going down a 10 Newton force. Now it's important here to define what's positive and what's negative. And since it's usually convention in math to say that up and to the right is positive, we'll just say that up and to the right is positive, okay? So if it's up to the right, it's positive, down to the left, it's negative. All right, now horizontally, we have these two forces. We have tension 2 times cosine of 30 degrees going that direction, and we have tension 1 times the cosine of 45 degrees going that direction. Now that point is not moving, right? Which means that if there was not an equilibrium, it would mean that the force pulling the thing to the right is greater than the force pulling the thing to the left, and it would be moving. It would not be static, okay? So how do we go about doing this? Well, we can write this statement. The sum of all the forces acting on this thing in the x direction, so sigma capital F sub x, is equal to 0. So let's write that now. Let's add up all the forces in the horizontal direction and set them equal to 0. So here we go. Remember what we said about positive and negative. We've got negative T1 times the cosine of 45 degrees plus T2 times the cosine of 30 degrees. That is equal to 0. Okay, we can actually, because we have two unknowns here, let's solve this equation for one of these unknowns. You could choose which one. Since one of them is negative, I want to make everything here positive, so I'm going to add T1 cosine 45 degrees to both sides, and I'll end up with this. T2 times the cosine of 30 degrees is equal to T1 times the cosine of 45 degrees. Okay, and I'm going to divide both sides by the cosine of 45 degrees. That will solve for T2. So T2 is equal to T1 times the cosine of 45 degrees divided by the cosine of 30 degrees. Okay, cool. Now, because of this statement, we know it's not moving left to right. But since it's static, it's not moving at all, we know it's also not moving up and down. So same thing. The sum of all the forces in the y direction is equal to 0. So let's sum up all the forces and set it equal to 0. So here we go. In the y direction, we had T1 is positive, right? T1 sine of 45 degrees plus T2 times the sine of 30 degrees, okay, minus 10, that's equal to 0. Okay, cool. Now notice what we have two equations and two unknowns. That's enough to solve. And we already conveniently solved for T2 in our first equation. So let's take this T2, this whole thing right here, and plug it in right there. Okay, and then we'll only have T1. All we need to do is solve for T1, then plug that back in and solve for T2. Okay, so here we go. We're going to now actually do the math part of this. Well, not the math, just the algebraic manipulation part of this. Okay, so let's do this in green. We're looking at this equation, and we're going to substitute in. So we have T1 times the sine of 45 degrees plus, now remember, we're going to sub in that thing we have for T2, which was T1 times the cosine of 45 degrees. I don't know what this little red line is, sorry. Okay, divided by the cosine of 30 degrees times the sine of 30 degrees. Okay, and then I'm going to also just add the 10 to both sides here to set this equal to 10, because we're going to have to do that later anyway, so might as well do it now. All right, now notice what we have here. And you don't have to recognize this, because ultimately you're going to have to plug this into your calculator to get the answer, but it can be helpful to simplify the process regardless. But I have, in this statement right here, I have sine of 30 degrees divided by the cosine of 30 degrees, right? Sine divided by cosine, that's tangent. So that's the tangent of 30 degrees. This is simplifying. You don't need to do this. But what that gives you is this, T1 times the sine of 45 degrees plus T1 times the cosine of 45 degrees times the tangent of 30 degrees. That equals 10. Now, we're trying to solve for T1. T1 is the only variable, the only unknown here. So we can solve for it. To do that, factor out the T1. Okay, so T1 times the sine of 45 degrees plus the cosine of 45 degrees times the tangent of 30 degrees. That equals 10. Now, at this point, because 45 degrees and 30 degrees just so happen to be nice, convenient angles that we know the exact values of, the exact sine, the exact trigonometric ratios for sine, cosine, tangent, cosecant, secant, cotangent, we could substitute that in right now if we wanted. And if we did, it would look like this: square root of 2 over 2 plus the cosine of 45 degrees is square root of 2 over 2 times the tangent of 30 degrees is square root of 3 over 3. Okay, and then we would divide both sides by this garbage here. So T1 is equal to 10 divided by, this would simplify down to be something like 3 root 2 plus 3 root 2 plus the square root of 6 divided by 6, something like that. Anyway, when you have to plug this into a calculator at the end of the day, because you can't just tell somebody that the tension in cable 1 is 10 divided by square root of 3 plus 2. They would look at you and slap you and tell you, what's the tension? Okay, well, it would be, when he plugs into a calculator, it turns out that it is 8.97. 8.97 newtons. Newtons, by the way, newtons, the units of newtons are kilogram meters per second squared. Okay, it's a mass times an acceleration. But you don't need to know that for math. That's a physics thing. Okay, so 8.97 newtons. Now, if we wanted to find what T2 was, notice that we have an equation for T2. It's right here. And now we just found T1, so we would plug that back in. So T2 then, and this 8.97 is rounded. We should have, by plugging this into the calculator, you should have the exact value of T2. Of T1. Do not use 8.97 when calculating T2. You have the exact value in your calculator, like however many decimals your calculator gives you. Use it. Okay. We'll talk about how to do that, the key presses at a later time. So we have this value for T2, which is 8.97. In fact, it's actually not 8.97, right? It's let's see. Let me see what this would be really quick. It's 10 divided by the sine of 45 plus cosine 45 tangent 30. Oops, I am in radians. That's not good. Hold on, mode. Set up. It is 8.965 something. 8.96575 ... Okay, that is T1, right? Times the cosine of 45 degrees. Cosine of 45 degrees divided by cosine of 30 degrees. Okay, that is going to equal, rounded, 7.32 newtons. Okay, so there we go. We found from nothing, just from giving this diagram, we found the tension in both of those cables. This process you will be asked to do several times, because it's a good way for teachers to know that you totally understand the process of breaking down a vector given, not even given its magnitude, right, but given its direction and essentially its magnitude. Can you come out with the components, and vice versa, right? Same thing. Okay, it covers kind of everything. It's a really nice type of problem.